Welcome to the course Engineering Mechanics Statics Part 2. Thank you so much for enrolling. This is a direct continuation of the course Engineering Mechanics Statics Part 1. I highly recommend to cover that course first before moving on with this one. This course will take the knowledge from the previous course and really put it into practice. Here are the topics that we will cover here. We will start with rigid body equilibrium problems in 2D and 3D. You will learn how to calculate support forces and moments for all kinds of structures, like a wing of an airplane or the support structure for flags. We will then cover the topic frames, pulleys, and machines, in which we study how forces are transferred from link to link in multi-member bodies such as an oil pumping unit or an excavator arm or the arm of a steer loader or a pulley system. Then we'll cover virtual work and equilibrium stability for mass spring systems. Looking at this container, you can analyze it using classical Newtonian mechanics, or alternatively, you can use virtual work there. That's what you will learn in this section. We will continue with friction forces, and not only you will learn how to analyze friction between surfaces of two different objects, but you will also learn how to analyze it when you have a rope wrapped around a circular object, like for example in this case where the car is lowered down at a constant velocity, or in this case where you have two blocks on top of each other and then you have a rope that connects them and that goes around a fixed peg. And you will also learn how to calculate the rolling resistance for a wheel when it's in motion. Finally, we will cover structural analysis for rigid bodies. We'll go over trusses, shear and moment diagrams for this moving crane, and cables that hold a suspension bridge in place. So these are the topics for this course. But the story will not be over. The next logical step from statics is dynamics, and I really encourage you to explore that fascinating topic. I do want to stress this. This is a highly active problem-solving course. I will be giving you problems and some tools to solve it. Then, it's very important that you at least try solving them first by yourself, and only then you should watch the solution videos. That's the best way to master this topic. Finally, if you find that the lectures go a bit too slow for you, then I recommend watching them at 1.25 speed. Good luck, and I wish you great learning experience. Thank you. Welcome back. Suppose that I have a rigid beam here. It's at rest in equilibrium. I apply a 4 kN force to it, as shown in the image. Let's neglect the force of gravity of the beam. It's small compared to other forces. You know that the beam is not moving anywhere. It's totally at rest. It means that this 4 kN force here, it needs to be cancelled by other forces. And it is. As you can see, at points A and B, you have two supports that hold the beam in place. If you think of the beam as a separate entity, then it only interacts with the rest of the world, in other words, with the ground, at these 2 points, A and B. These two supports keep the beam in place where it is. The forces at the supports at points A and B are the following. You have a horizontal force at point A that the ground applies to the beam through the spin. Then you also have a vertical force at point A applied to the beam by the ground, and then you also have a force here at B, which is perpendicular to the ground, and since this ground here is tilted 30 degrees, that means that you also have 30 degrees here. And so these forces, AX, AY, and B, they are generated due to this 4 kilonewton vertical downward force. And these forces, AX, AY, and B, they keep the beam at rest. Without those forces, the beam would accelerate downwards because of this 4 kilonewton force. And if your center of mass for the beam is anywhere else but here on the line of action of this 4 kilonewton force, then the beam would also rotate. But these forces, AX, AY, and B, they prevent the beam from doing that. These forces are called reaction forces. They react. Since we assume no force of gravity for the beam, if you don't have this 4 kilonewton force, then there are no reaction forces. The forces AX, AY, and B, they are only generated because I apply this 4 kilonewton force at that beam in a specific location. Here I have another example as a Python animation where you have a beam and I apply a force on that beam in the middle of it. And because of that, I have two reaction forces, one on the left and one on the right. If I don't have that applied force, I don't have the reaction forces. The bigger my applied load, the bigger the reaction forces. Now, the question is, what are AX, AY, and B? Why would you need to know that? If I apply a different load to the beam, let's say instead of 4 kilonewtons, I apply 6 kilonewtons, then the reaction forces would adapt. You would have different AX, AY, and B, and the beam would stay at rest anyway, right? Well, not quite. Everything has a limit. The supports at point A and B are made of some kind of material. For example, if you look at this specific support at point A, then in 3D, you see that there is a pin there. If it experiences too much force, it will break, and your structure might collapse because of that. This pin here, it might simply break. That's why you need to be able to calculate the reaction forces. Once you know these support forces at A and B, you can then make an educated selection in choosing a pin that is strong enough to withstand the required loads. In Statics Part 1, we had a section in which we solved particle equilibrium problems. We had lots of structures with cables. There, we used force equilibrium principles to solve for forces that cables had to endure. That allowed us to choose the cables strong enough for the required loads. However, the situations that we had there were set up in such a way that the lines of action of all the forces would intersect at one point. Let's say here at point C. And because of that, it was the same like applying all the forces to a particle. There was no tendency for the body to rotate. You did not have to think about the size of the body, about its dimensions. That's why, in particle equilibrium problems, the necessary and the sufficient condition was that the sum of all the forces in all the directions had to equal 0. So the sum of all the forces in the x direction had to be 0. In the y direction, it also had to be 0. And the same thing in the z direction. This condition was necessary, meaning that it absolutely had to be met. And then it was sufficient, meaning that you did not need anything else to achieve this equilibrium. With that, you could find the forces in cables and know if they were safe enough. However, if you look at this beam now, then now you cannot treat it as a particle. Here the size of the body matters, and it also matters where you put this force. You can have the same force, 4 kilonewtons, but if you apply it in a different location on this beam, then the reaction forces also change. So the same 4 kilonewton force, but you simply move it to another place, and you have different AX, AY, and B. So here we are not dealing with particle problems anymore. If this is my beam, and I forget about the reactions, then if I apply 4 kilonewtons to the center of mass, then the beam will only accelerate in the direction of the force. But if I apply the same force to another location, let's say d meters from the center of mass to the right, then the center of mass will still accelerate in the direction of the force. It will still go down along this straight line, but you will also have angular acceleration alpha, because you will have a moment about the center of mass, and this moment will be 4 times d clockwise. It means that the condition where the sum of all the forces in all the directions, it's still a necessary condition, but it's not a sufficient condition anymore. In the first case, if I apply a 4 kilonewton force directly to the center of mass of the beam, then this beam would be in equilibrium if it had a 2 kilonewton force here and here. And that's because these two upward forces, they will cancel out this 4 kilonewton downward force. That's because 2 plus 2 equals 4, so you would have 4 kilonewtons up and 4 kilonewtons down. And so the sum of all the force vectors would be a zero vector. And this is just a compact way to write all this here. But now, if we place this 4 kilonewton downward force d meters away from the center of mass, and I still have 2 kilonewtons here and 2 kilonewtons here, then this force condition is still met. All the forces will cancel each other out. That's why the center of mass will not accelerate anywhere. But the beam is not in equilibrium. It will either start rotating about the center of mass, because remember, in this case, you have a moment which is 4 times d kilonewton meters, or if it can't, because let's say that you have some kind of supports here underneath the beam, then in that case, these two reaction forces, they would simply be wrong. In this particular case, you would have a bigger reaction force here and a smaller reaction force here. In other words, if I put this 4 kilonewton force away from the center of mass, then I will have a moment about the center of mass, and moments create the tendency to rotate. So this beam will have the tendency to rotate clockwise, and that's why you have a bigger reaction force on the right and the smaller one on the left. If you take this one and you add them together, you will still get 4 kilonewtons up. But now, your reaction forces also need to fight against this tendency to rotate, not only the tendency to accelerate. And that's why those reaction forces must be bigger in some places and smaller in other places. It means that this condition here, the sum of all the forces needs to be zero in all the directions, is necessary to keep the beam at rest, but it's not sufficient. It's not enough. This condition only makes sure that the center of mass of a body does not move anywhere. We need another condition that does not allow objects to rotate. Since moments make objects rotate, the additional condition is that the sum of all the moments in all the directions must be zero. So now we also need to have this condition. Or I can also write all the moments about the x-axis must be zero, all the moments about the y-axis must be zero, and all the moments about the z-axis must be zero. This condition here will prevent the body to rotate. These two conditions, the sum of all the force vectors needs to be a zero vector, and the sum of all the moment vectors needs to be a zero vector. If they are met, then they are necessary and sufficient conditions to keep a body in equilibrium. And also, it does not matter what point I calculate moments about. For example, consider a random body. The sum of all the forces is your resultant force Fr. Let's say that it's 0 newtons. It's a zero vector. We apply it to point O. We also calculate all the moments about point O and then add them up. So we have a resultant moment vector about point O, and it's also a zero vector. So both the force and moment conditions are met. So the body is in equilibrium. If I now take point A and I calculate a resultant moment about point A, then I can do it like this. From A, I will have a position vector r, and so my resultant moment about point A equals the resultant moment about point O, which is this one here, plus the position vector cross Fr. But now remember, this one, it's 0, and your Fr is also 0. So your Mr about point A will still be 0. Even though your position vector is not 0, but if you cross it with a force vector that is 0, then this entire second term will be 0. And then your first term is also 0. So you will end up with 0. And so when we use these two conditions to solve equilibrium problems, then these are called rigid body equilibrium problems. Not particle, but rigid body equilibrium problems. Note that here we are still assuming the rigid body condition. It means that the bodies, like this beam, we assume that they do not deform when subject to loads. In reality, all bodies deform a bit. So when you use rigid body equilibrium principles to find reaction forces, then just know that it's not the complete truth. However, when deformation is very small, which is the case with most beams and other structural elements, then the error in our calculations is very tiny, and we can accept the approximated results that you got from using the rigid body equilibrium principles. Welcome back. So how do we actually approach rigid body equilibrium problems now that we know what conditions must be met? Well, just like with particle equilibrium problems, we start with a free body diagram. We sketch the shape of our body, in our case the beam. We define our positive x and y axis, and then we list all the external forces that the body is subject to at the location that they are applied, and also all the external couple moments that are applied to the body. We don't have a couple moment here, but in general, you can also have a couple moment. Now note that I say external forces and moments. You can also have internal forces and couple moments. For example, let's say that I have 3 beams here. In the first case, I apply a force to the beam horizontally. Then here, I apply it vertically. And here, I apply a couple moment to it. And now, I will mentally cut the beams. In that case, if this is my external force that I applied to the beam, it's this one here, then in order to keep this piece in equilibrium, I have to have the same force here, but opposite in direction. But due to Newton's third law, I need to have the same force here that is opposite to this one here. But they all have the same magnitudes. And the same thing here, I have this vertical external force, F, but this piece needs to be in equilibrium. Otherwise it would start moving. So I have to have this force cancelling the external force. And due to Newton's third law, I have this force here in the opposite direction. And the same thing here. If I apply a counterclockwise moment to this piece, but you know that this piece is at rest, it's not rotating, it means that you need to have another couple moment that has the same magnitude but has the opposite direction. It needs to be here in order to keep this piece in equilibrium. But due to Newton's third law, you have a couple moment here as well. So these two couple moments at the location where you had cut the beam, they will cancel each other out. And so these forces and moments here, they are internal. They only appear when you mentally cut the structure and you want to draw free body diagrams to those individual pieces here. But at the cutting point, due to Newton's third law, action-reaction, this force is always cancelled out by this force. Also this one is cancelled out by this one, and this moment is cancelled out by this moment. It has to be like that. If the left piece applies a force to the right piece, then the right piece applies a force to the left piece with an equal magnitude but opposite in direction. And the same is true for the moments. And so you can see that the internal forces and couple moments, they simply cancel each other out. That's why there is no point to include them in the free body diagram. And by the way, the reaction forces such as AX, AY, and B, they are also external forces. These are the forces that the external world applies to this beam through these pins at A and B. And now, when we draw our free body diagram, then when listing the reaction forces at the supports of a body, we have to pay attention to what kind of supports we are dealing with. You see, there are different kind of supports that generate reaction forces in different direction. For example, our beam has two types of supports. The one at A, it's called a smooth pin support, and the one at B, it's called a rocker support. When dealing with those supports, you have to use your imagination and visualize how this support restricts motion. You can restrict two types of motion, translational and rotational. Now, if you look at our two supports here, the smooth pin and the rocker support, do they restrict rotational motion? The answer is no. if there is nothing else, then this beam here can freely rotate in this direction or in this direction about this pin that we can call A. So that's for the smooth pin support. And the same thing with the rocker support. If there is nothing else, then the beam can freely rotate in both directions about this pin, let's call it B. Therefore, there is no reaction moment in those supports because they provide no resistance to rotational motion. Of course, in reality, there is always a bit of internal friction between the pins and the rest of the structure when you rotate that structure about the pins, but this is not real resistance. You cannot count on it in order to stabilize a structural element. This internal friction is too small for that, and it's not even supposed to be big. It might be necessary for you to allow this rotation. However, if you look at the smooth pin here, then you can imagine that it restricts translation in all directions. This support is fixed to the ground. You can rotate something about the pin, but you cannot change the location of this pin. You cannot just take this element, right, and translate it here. You cannot do that. Therefore, this pin provides resistance to translation in all directions. Therefore, this pin can generate reaction forces both horizontally and vertically. And that's what you need to put on the free body diagram. The reason why I have AX and AY here is because no matter what external forces or moments I apply to this beam, I know that this location at A, it will stay here where that pin is. The beam might rotate about this pin, but it will be fixed to this location here. And again, note that we are talking about the forces that supports apply to the beam. Due to Newton's third law, the beam applies forces to the support that are equal in magnitude but opposite in direction. And so every time I draw it like this, or in this case like this, that's this case here where the support applies forces to the beam, not the other way around. This would be false. When I have a body and I draw a free body diagram for it, and I list all my reaction forces and moments to that body, then those reaction forces and moments are the ones that the supports apply to the body itself. What about the other one, the rocker? Well, it allows rotation about this pin B, but it also allows translation along the surface. Of course, you might have a little bit of friction between the surface and the rocker support, but this friction force can be too small in order to be taken into account. If we assume no friction between the rocker and the ground, then the rocker can freely translate along the surface. It only restricts motion in the direction normal to the surface. That's why this particular support, the rocker, it generates a reaction force normal to the surface. And that's what you need to put on your free body diagram. And again, you have Newton's third law here. What you put on your free body diagram, that's what the rocker applies to the beam. And then the beam applies the same force, but in the opposite direction to the rocker. And there is a reason why supports like a rocker is used. You know that the rocker does not restrict rotation about this pin B. So it has the ability to adjust itself a little bit, where instead of the beam rotating about this pin B, in fact, the rocker rotates a little bit about this pin B. And it can be useful because when temperatures change, then the size of your structure slightly changes. In summer, when it's hot, the beam expands. And in winter, when it's cold, it contracts. If you restrict the beam with smooth pins from both sides like this, then this repetitive expansion and contraction over time, it will damage the structure. You can imagine that in summer your beam becomes bigger, but these pin locations, they are fixed in one place. And that causes internal stresses inside the beam that damage the structure over time. That's why in many cases, one side of the structure is not completely fixed. As the rocker rotates about this pin, the location of the pin can translate a little bit along the surface when the structure expands or contracts due to temperature variations. Of course, one side of the structure needs to be fixed in one place, like in this case A. If you allow both sides of the structure translate, then you might make the entire structure unstable. There is another type of support called the roller. It is usually drawn like this. You have small wheels here, and it works on the same principle like the rocker support. You have a pin here. The beam can rotate about this pin, so it does not restrict rotational motion. It does not restrict translational motion along the surface either, so it can roll along the ground. It only restricts motion normal to the ground, perpendicular to the ground. It can be used in bridges, for example. Here you have a smooth pin support, so translation in all directions is restricted. And then here you have a roller where translation only normal to the surface is restricted. This configuration allows one side of the bridge to move horizontally in order to cope with the bridge's size change due to variations in temperature. And now, your task is to take our initial beam situation. You have all the dimensions here. You can neglect the force of gravity of the beam, and you have to calculate the support forces at points A and B using the rigid body equilibrium principles. So good luck, try it out by yourself first, and then see the solutions in the next video. Thank you very much. Welcome back. So let's now find our reaction forces AX, AY, and B. You know that at point A, translation is completely restricted. That's why you have reaction forces both in the X and Y directions. At point B, you have the rocker. So motion can happen along the surface, but not normal to the surface. In both cases, A and B, rotation about their pins is possible. That's why there are no reaction moments there. And now, all we have to do is to apply our two equilibrium principles. The sum of the force vectors needs to be 0, and the sum of the moment vectors needs to be 0. First of all, let's take this reaction force B and decompose it into its x and y components. So Bx equals B times sine 30 degrees, which is 0.5 times B, and By equals B times cosine 30 degrees, and it's this result here. Then, let's apply the equilibrium conditions. Let's first do it for the forces in the x direction. You have Ax minus Bx, that's gonna be 0. In other words, I can write it down like this. Then let's do it for the forces in the y direction. Here they are, or here. And finally, That's something that you did not have in the particle equilibrium problems. You will take a moment about a point. In this case, I'm going to take it about point B, and all the moments about this point, plus all the couple moments, they must be 0. Remember, I can take my moments about any point I want. So it makes sense to me to choose a convenient point. Point B is very convenient because the lines of action of AX, BX, and BY go through point B. So their moment arm, and therefore the moments caused by those forces, are 0 kilonewton meters. So you only have to find the moments caused by forces of AY and this 4 kilonewton downward force. So I will have 4 times 2, 4 is in kilonewtons, and 2 is in meters, because the moment arm here is 2 meters, minus AY times 8 meters. And that must be 0 as well. So you will have 8 minus AY times 8, and that must be 0. AY gives you a clockwise moment, so it's negative, and then the 4 kilonewton force gives you a counterclockwise moment, so it's positive. And now you have 3 equations and 3 unknowns. 1, 2, which is also here, and then 3, which is your B. So you can find the unknowns. From the last equation, you have 8 times AY equals 8. So AY equals 8 over 8. That's 1 kilonewton. Then in the second equation, you can rewrite it like this. You know that AY is 1 kilonewton. You can also get rid of this one here if you put it here like this in reverse. And so B will equal 6 over square root of 3 kilonewtons. Finally, the first equation gives you AX equals 0.5 times B, then 0.5 times 6 over square root of 3, and that's 3 over square root of 3 kilonewtons. There you go. You have your answers, and they're all positive. What does it mean? Well, like we discussed in the previous part, in statics part 1, it means that all our assumptions about the directions of the unknown reaction forces were correct. A negative answer would have told us that the reaction force is in opposite direction to what we had initially assumed. And so we have found the reaction forces that appear because of that 4 kilonewton vertical downward force that is applied in this location, 2 meters from point B and 6 meters from point A. And we used the rigid body equilibrium principle to do it. Thank you very much.